Let's talk gas laws. When we talk about gases, we have several different variables that we take into consideration. When we put all of our gas law stuff together, what we'll ultimately end up seeing is something that looks like this. PV equals nRT, where we have pressure, volume, so P and V, N is moles, R is a constant, and T is the temperature. Okay. Now, there's some really important things to keep in mind when we're dealing with these various different variables. Okay. I can take R and I can rearrange it to have PV over NT. And so we're going to look at different relationships where we just look at pressure and volume, where we look at pressure and temperature, where we look at volume and moles, and see how two of the variables interact with each other. Okay, now a few things to keep in mind too, are we have to be in specific units. P is either going to be atmosphere or torr. V is in liters. N is moles. And temperature is in Kelvin. Okay, so these are the important units that we use when we work with any of our gas laws. All right, so we're going to look at Boyle's, Charles's, Gay-Lussac's, Avogadro's, and a combined gas law before we get into our ideal gas law. All right, so Boyle, he studied the relationship between volume and pressure. Okay, so volume and pressure are an inversely proportional relationship. When one goes up, the other one goes down. So what we get is this image here if we graph our volume versus pressure. It's not a linear relationship. It's exponential because it's an inverse relationship. It gets this little curve there, okay? And so we have to graph volume versus 1 over pressure in order to get a nice linear relationship as shown over here. Because if we have a linear relationship, we can get the equation of a line and we can extrapolate things, okay? So Boyle's law, again, pressure and volume. Okay, and so if pressure goes up, volume goes down. If volume goes up, pressure goes down. Inversely proportional relationship. Okay, and so as volume increases, pressure decreases. As volume decreases, pressure increases. All right. Okay, so we can do a problem here. Because we're dealing with these two variables, what we can do is we can do a condition 1 equals condition 2. So what we're going to do for this is we're going to take P1 V1 is equal to P2 V2. So if I know the pressure and the volume of condition 1, and I know, say, the pressure of condition 2, I can solve for the volume of condition 2. Or if I have any three variables, I can solve for the fourth. So my problem tells me that I have a balloon at a volume and a pressure. So my P1 is 1.0 atmospheres. My V1 is 0.55 liters. Okay, we're going to raise the height where we're going to get a pressure. So we'll do our second pressure is 0.4 atmospheres. And we want to know the final volume of that balloon. Okay. All right, so we're going to solve for V2. So if I rearrange this for V2, V2 is going to be P1 V1 over P2. Okay, so since I defined my variables, now it's easy to plug them in. So 1.0 atmospheres times 0.55 liters over 0.4 atmospheres gives us 1.375. We have two sig figs, so we're going to get 1.4 liters. Okay, so the pressure went down and the volume went up. Okay, our next is Charles's law. All right, so Charles is looking at volume and temperature. So Charles says that at a constant volume, or at a constant pressure, the volume of a fixed amount of gas is directly proportional to the absolute temperature. Okay, so what we're saying here is we've got a relationship. We've got volume 1 over temperature 1 will be equal to volume 2 over temperature 2. And these are directly proportional. So when volume goes up, temperature goes up. When volume goes down, temperature goes down. It's a nice linear relationship. Okay, so if I lower the temperature, I'm going to lower the volume of my gas. If I raise the temperature, I'm going to raise the volume of my gas. Okay? All right. You can see this if you play with the balloon and liquid nitrogen. Liquid nitrogen is super cold. So if you pour liquid nitrogen on the balloon, it gets super cold and the balloon shrinks in because all the air in it gets closer together, so the volume goes down. And then if you move the liquid nitrogen out of the way and let it warm back up, the balloon will re-expand. You can do this a bunch of times. You can't do it infinitely because the rubber on the balloon doesn't survive an infinite number of times of doing this, but you can do it several times before the balloon eventually decides, all right, you've stressed the rubber enough, I'm done. Okay, so nice directly proportional relationship there. Okay, and so what happens is at a higher temperature, we get more collisions, and so we end up with a larger volume because everything's moving around faster at higher temperature. Okay, so we can try a problem here. Okay, so again, we have our V1 over T1 is equal to V2 over T2. Okay, so I have some argon that's going to be heated from one temperature to the next. All right, so my volume 1 is 452 milliliters. My first temperature is 22 degrees Celsius. I don't know the final volume, so that's our question mark. And my temperature 2 is 187 degrees Celsius. Okay, now remember, for these, we need liters for our volume, and we need Kelvin for our temperature. All right, so we're going to convert this. So we're going to take 452 mils. We get 1 liter in every 1,000 milliliters. So we're going to get 0.452 liters. Okay, going from Celsius to Kelvin, we're going to add that 273.15. And so we're going to get 295.15 here. We'll do that down here as well. I missed a number. Okay, and so our second temperature becomes 460.15 Kelvin. All right, now when we solve this, okay, what we're trying to solve for right now is our V2. So if you're shaky on the algebra, what we can do is we can do a cross multiply. So if I cross multiply these, I'm going to get V1 T2 is equal to V2 T1, okay? We need to isolate V2 because that's the variable that we're solving for. So to do that, I'm going to have to divide both sides by T1. So I'm going to ultimately end up with V2 is equal to V1 T2 over T1 because T1 will cancel out on that side, okay? So now this is where it's really important that you took the time to define your V1 and T1 and V2 and T2. Because now I have to pay attention to which one goes where. Because I have V1 times T2 divided by T1. So it's really important to pay attention to what you have where. Okay? All right. So what we're going to do is plug it all in. So my V2. So V1 is my 0.452 liters. My T2 is the 460.15 Kelvin, and my T1 is the 295.15 Kelvin. Okay? All right, and then we do the math, and we get 0.7047 equal to 0.705 liters. All right, our temperature went up, and indeed our volume also went up. All right, now our next one is Gay-Lussac's law. So in Gay-Lussac's law, we're looking at the pressure exerted by a fixed quantity of gas at constant volume is directly proportional to the absolute temperature. So this one is similar to the last one, except instead of volume and temperature, it's pressure and temperature. So P1 over T1 is equal to P2 over T2. Directly proportional, so when pressure goes up, temperature goes up. If one goes down, the other one goes down. Okay, and so you can see here I have 300 Kelvin and 1 atmosphere. Now I have 600 Kelvin and 2 atmospheres. All right, and so what's happening is we get a higher pressure at higher temperatures because everything's moving around more. So it's bumping into stuff more, which gives us a higher pressure. If I cool it down, it's not going to be bumping into each other as much, and so we're going to get a lower pressure. All right, and so this one also is directly proportional, okay? All right, so this one is very similar to the one that we did a minute ago, except instead of solving for V2, this time you're going to solve for P2. So I'm going to start you off. All right, so we have a bicycle tire, 2000 torr at 38 degrees Celsius. And if you take it over to Lake Tahoe, where it's going to be our new pressure at 0 degrees. Okay, so our P1 is 2000 torr. Our T1 is 38 degrees Celsius. Our P2, we don't know. Our T2 is our 0 degrees Celsius. And again, it's P1 over T1 is equal to P2 over T2. Okay? So, pressures in torr, that's fine. You can use atmosphere or torr. But the temperature, what does temperature need to be in? It needs to be in Kelvin, all right? So you're going to get 311.15 Kelvin and 273.15 Kelvin. All right, and so now what you want to solve for is P2. So P2 is going to be P1 T2 over T1, okay? So I'm not going to plug the numbers in. I want you to try. I set it all up for you. See if you can plug the right numbers into the right spot. All right. If you did it correctly, you should get 1,756 torr, which indeed 1,756 is lower than 2,000. So there's our directly proportional relationship. Okay. Avogadro's law starts looking at moles. So if you think about your lungs, okay, this goes into play very well with your lungs. So if I breathe in, I'm taking in more air, so I have more moles of air, and so my lungs expand. The volume gets bigger. When I exhale, I'm getting rid of moles of air, and my volume gets smaller. Okay? And so we can look at volume 1 over moles 1 is equal to volume 2 over moles 2. Okay? All right. And so here, if I start off with 0.1 moles and I increase to 0.2 moles, my pressure or my volume is going to go up. Okay? If I'm at a fixed temperature and pressure, if I have equal volumes of an ideal gas, we'll have equal number of particles. Okay, so equal volumes of gas, equal particles. All right. All right, so Boyle's law, inverse relationship, everything else directly proportional. When one goes up, the other one goes up. When one goes down, the other one goes down. Okay, so here is my challenge to you for 3 variables. We've got a bubble at the bottom of a lake where the pressure and the temperature are 8 degrees Celsius and 4 atmospheres. This bubble is going to rise to the surface with a pressure and temperature of 1 atmosphere and 25 degrees Celsius. We need to know the final volume of the bubble if the initial volume was 21 mils. Okay, so we had a pressure 1 is 6.4 atmospheres. We had a temperature 1 of 8 degrees Celsius. We had a volume 1 21 mils. Okay. We had a pressure 2 of 1.0 atmospheres. Temperature 2 of 25 degrees Celsius. And we don't know that second volume. Okay. So remember, when I started off this video, I showed you that PV equals nRT, and I solved it for R, and I had PV over NT. So here I have PT and V. So this one is going to look like this. P1 V1 over T1 is equal to P2 V2 over T2. Okay? All right. We've got some converting to do. We need Kelvin, so this converts to 281.15. This converts to 298.15. Then we need liters, so this will convert to 0.021 liters. Okay, so you want to solve this particular problem for this V2. All right, so if you rearrange it to correctly, you should get V2 is equal to P1 V1 T2 over P2 T1. Okay, so again, really important to have those variables defined so that you know where all the 1s and 2s go so you don't get them mixed up. Okay, so I want you to plug this all in, set it all up. Again, I got you this far. All you have to do is plug the right numbers into the right places. Okay, and if you do it correctly, you should get a new volume of 0.14 liters. Okay, so these are our individual gas laws. And it was these experiments looking at how two of the variables interacted with each other that let us figure out how all of the variables tied in and fit with each other.